Hello, welcome back to what should be a short one. We've looked at general rotation, we've looked at triangles, and so now we are going to put the two things together and make triangles for general rotation, producing therewith the trigonometric functions of general angles. The reason why we got to do that is because with right triangles, you have a triangle, obviously. The angles add up to be 180 degrees. In total, you have 90 of those degrees spoken for in the right angle, so you have at most 90 degrees for either of the remaining angles. Obviously not exactly, but as much as slightly less than 90 degrees. That's a bit of a problem though, because trigonometric ratios are defined for everything, or at least they should be, right? Because on the unit circle we had things like sine of 1,000 degrees, or sine of 9 pi over 4, or sine of 7 pi over 12, or something like that. We had sines and cosines and tangents defined for angles, for rotations, for movements that are far beyond just the first quadrant. And so we need to be more general. We need to make sure that what we have done so far this unit does indeed mesh with everything we did in the previous unit. So here's the results we had previously, but let's go ahead and get this going here. So again, I have my circle, my unit circle anyway, in the middle there, and I am moving around some other rotation amount, and we could inscribe a triangle that was always acute by dropping a vertical or raising a vertical to or from the x-axis. Well, what we need to do now is make sure that our appropriate right triangles that we're inscribing can still produce the sine and cosine values that we are already used to. Sound good? Because here is the issue, right? These results, again, if you were to look at them again, for radius r and angle rotation theta, we have these results. Cosine of theta was x over r, sine of theta was y over r, tangent was y over x, secant and cosecant cotangent we all had defined appropriately. But what about no r? What is sine of 60 degrees? Or what is sine of 120 degrees? Or what is sine of 135 degrees? These are all couched with some radius. So how do we go to just having sine angle equals number? The way we got to do that is bringing everything together. See, here's what has to happen. And it's not just for any angle, not just for acute angles, but for every angle. What we're going to do in this video is look at, say, tangent of 135 degrees or secant of 120 degrees. That's going to be our motivator here. And the way we're going to find what these are formally is not worry about r necessarily, just worry about the ratio accordingly and get numbers from that. So the way we're going to do that with everything together is we're going to do our rotation, we're going to inscribe our triangle, but instead of calling the interior acute angle theta, right, theta was our angle of rotation, instead we're going to call the interior acute angle theta bar. That's going to be our reference angle. And then we can find the trig ratio for theta bar using our right triangle approach, and then we can apply the appropriate SIGN sign, the plus or minus, to our trig function by recognizing what quadrant we're in. So let me show you what I mean. Right here is my general rotation. I do have a point here as before, but we don't truly need that. But as we're rotating around, we're ending up somewhere. And wherever we choose to end up, we can inscribe a triangle, just as I mentioned earlier. And you'll note also that the base of this triangle is not necessarily equal to the original radius, which should make some amount of sense because the original radius is spoken for in the hypotenuse, and so the base can possibly be as big as the radius, but it probably won't be. In fact, the only time it ever will be is when we're at 0 or at pi. Otherwise, never. But as we're going around, we are going to end up somewhere. So let's say we're going to rotate by 135 degrees clockwise. 135 degrees in radians is 3 pi over 4. So there I am. This angle here from start to finish, from initial side to terminal side, is 135 degrees. So from here to here, I go 135 degrees. And so the supplement of that angle, which is down here now, right, because the whole rotation from 0 to pi, from 0 to 180 degrees, speaks for x to x-axis, that means this has to be 180 minus 135, or 45 degrees. So now I have a right triangle of some radius with the interior angle being 45 degrees. And now we can handle that. We know the ratio of any right triangle with interior acute angle of 45 degrees has to be 1 to 1. Right? Because for any radius r, this being a special triangle, this has to be r divided by the square root of 2. And this has to be r divided by the square root of 2 for any radius r. So the tangent of 45 degrees has to be 1 because it's the ratio of opposite to adjacent. Opposite to adjacent, there we go. So we've got that going for us. So we got tangent of 45 degrees being 1, but that is not tangent of 135 degrees. That is because we are in the second quadrant. Tangent is negative. Reference angles don't give us that. We have to do a little more. And so our little more is to apply the negative sign to say finally that tangent of 135 degrees is negative 1. Now, we have to do a little more because there are no right triangles with an interior angle of 135. Because that plus the right angle already exceeds 180. And of course, what if we go with an angle beyond 180? Or what if we have an angle that's negative? For instance, what we do now, secant being negative 120. So again, our rotation is now negative 120 degrees, which is now negative 2 pi over 3 in radians. So there is my rotation now. Let me rewrite this. So going from initial to terminal side, that's a rotation of 120 degrees. So our reference angle, our theta bar, is in here and is 60 degrees. And so now I'm working in a 30, 60, 90 right triangle. And it's going to be the case that the ratio of any side length, right, for any radius r, the ratio of any radius r to the appropriate side length for this angle is going to be the same, regardless of the size of my triangle. So, secant being 1 over cosine and my reference angle being 60 degrees, I know that that has to be 1/2 for my reference angle 60 degrees. Well, cosine is. Secant being 1 over that is now 1 over 1/2 is now 2. But we're in the third quadrant. Cosine is negative, so secant is negative. Therefore, secant of negative 120 degrees is negative 2. In short, the way you think this works is exactly how it works. Right? You could convert all these things to radian measure, and you would get the appropriate thing on the unit circle. Unit circle for rotation there is appropriate everywhere. So this does work exactly the way you might think it would. So we have the right shape of any triangle, and now we have the right shape of any rotation beyond just the first 90 degrees, beyond just the first quadrant. So we can now handle trigonometric functions for all angles using both the unit circle approach and also now the right triangle approach with reference angles. So that will bring us to what we'll be doing in the next set of videos. We'll start defining inverse trigonometry for right triangles, and then after that, starting the week after, I imagine, we will get into other triangles. So we will eventually, and very soon in fact, move away from right triangles and into general triangles, but we will worry about that later. So let me know if you have any questions, what you're wanting to see more of, what questions you have, what you're struggling with, and I will see you in our next class. Have a good one.